3, 2, 1.
Okay, good afternoon, everybody. Apologies for some ICT issues. Those of you who know me will realise I'm better with a sledgehammer than I am with a computer, so I do apologise. Thanks for joining us this afternoon for the webinar event, and we're kindly being joined today with Paul Christensen, who's a Professor of Electrochemistry, Lithium-Ion Battery Fires, and an advisor to the NFCC. I've heard Paul talk on numerous occasions on various different podcasts, and that was partly one of the reasons behind why I asked him to join us today. But I know Paul has been doing a lot of work with other fire services around the country, and I know he's done something with us in the past with South Wales. But hopefully you will enjoy the information that Paul will impart with us today. Just a quick bit of etiquette before we start. If you could use the Q&A section on Teams for all the questions, and then we'll go through the questions and ask Paul at the end of the webinar session. Other than that, I don't think there's anything else I need to inform everybody on, so I'll hand over to Paul and get this running as soon as we can. Thanks very much for your patience. Speak to you later.
Okay, I hope everybody can see that. So assuming everybody can see that, hello everybody. So my name's Paul Christensen, Newcastle University. My work is funded by the Faraday Institution, which was set up to create a lithium-ion battery industry in the UK about 4 years ago. So straight in, what's a lithium-ion battery? It's the simplest possible battery you can get. If you look at top right, it comprises a mixed metal oxide, in this case lithium cobalt oxide, smeared as an ink on an aluminium foil current collector, very thin, and then literally soot, graphite particles, smeared on a copper foil current collector. These are pressed tightly either side of a very thin porous plastic separator, soaked in a mixture of organic solvents called carbonates, lithium hexafluorophosphate, which dissolves to give you the lithium ions, and additives. Now we know what the list of additives comprises, but we don't know which additives are in any particular battery because they're commercial secrets. But a lot of them are toxic, some of them are cytotoxic, and lithium hexafluorophosphate itself will react with the moisture on your skin to produce hydrofluoric acid. So take a tip, don't splash the electrolyte on your skin. Notice that separator actually can be 15 to 30 microns. That's a fraction of the thickness of a sheet of A4, an A4 sheet of paper. Now, the vast majority of batteries you'll come across use a graphite anode, as it's called. So we call the batteries by what the cathode material is. Lithium cobalt oxide is an LCO battery. Now, they only like 3-letter acronyms. So lithium nickel manganese cobalt oxide is NMC. Lithium ion, or more correctly, lithium ferrous phosphate is LFP, and so on. Now, how do they work? When the battery is discharged, all the lithium ions are in that mixed metal oxide. So in this particular case, the lithium cobalt oxide. As you supply energy as electricity, lithium ions move out of the mixed metal oxide, through the solvent and the separator, and into the graphite particles, and electrons move around the external circuit. Now that's at a higher energy. So if you then discharge the batteries, the reverse happens. The electrons come out of the graphite particles, move through the solvent and into the mixed metal oxide cathode. It's so simple, it's called a rocking chair battery. But there has been nothing like it on this planet before. No other battery comes close to the amount of energy that can be stored in a very small space. Now, in my day, a battery was a battery. You had transistor radio batteries, you had torch batteries, etc. Nowadays, the battery is the largest unit. The smallest unit is the cell, which comes in 3 shapes and sizes, or form factors. Cylindrical cells are typified by the 18650 cell, 18 millimeters in diameter, 65 millimeters long. Prismatic cells are about the size of 2 20-cigarette fag packets joined along the long edge. And pouch cells are about the size of an A4 sheet of paper and about 1 centimeter thick. Cylindrical and prismatic cells are in metal cans. Pouch cells are just like glorified crisp packets. And only pouch cells were actually designed for electric vehicles. Cylindrical and prismatic cells were only ever designed for use in portable electronic applications. But all three form factors are found in all applications. Many cells make a string or a module. Many strings or modules make a battery or battery pack. Well, you've all heard of thermal runaway, which is the bad boy. And it all comes down to the fact that lithium-ion batteries should not exist. When you first charge a lithium battery and those lithium ions go into the graphite, that's at a much higher energy than the solvent. So immediately the solvent is attacked. And you generate hydrogen and methane and hydrofluoric acid gas and lots of heat. The heat speeds up those processes to produce even more gas and even more heat. And if that continued, the battery would just explode. The reason it doesn't is at the same instant, a protective layer forms around the graphite particles that acts like a prophylactic. It allows the free passage of lithium ions, but stops those highly energetic graphite particles touching the solvent anymore. That solid electrolyte interface is then responsible for all the subsequent problems. When it's eroded or damaged, those processes start again. Now, when a lithium-ion battery is abused by heating, crushing, penetration, overcharging, or by defects or contamination introduced at the manufacturing stage, that damages the SEI. And those exothermic heat-producing chemical reactions start again. Now, heat is produced exponentially, the red line, but it's only dissipated linearly. Moreover, heat is dissipated from the surfaces of an object, but it's produced throughout the volume of an object. So you can see, as you go from mobile phones to electric vehicles to grid-scale battery energy storage systems, the volume is getting bigger and that heat is being retained. Now, when those two lines cross, you will see a measurable temperature rise. And that's the easiest, simplest definition of thermal runaway. From 1 degree centigrade rise per second to 1 degree centigrade rise per minute. But a far better, more accurate definition is when those exothermic heat-producing chemical processes become self-sustaining and you enter uncontrolled positive feedback. And that almost certainly occurs before those lines cross. And at that point, essentially, you can't stop it. So this shows you a little video from abusing a small module. So when your cells are abused, they generate all these gases, hydrogen up to 50%, carbon monoxide, carbon dioxide, hydrochloric acid gases, hydrogen cyanide, small organic molecules like ethane, methane, etc. Now, when prismatic and cylindrical cells, their safety vents, blast caps, burst, and when a pouch cell bursts, those gases take with them small droplets of the organic solvents. Hence, the thick white appearance, which can be and has been mistaken for smoke or indeed steam. It's not. Smoke and steam are not explosive. And fires and explosions are occurring on land, on and under the sea, and in the air from lithium-ion batteries. Now, if you take nothing else away but the next slide, I'll have done some good. Use your common senses. Forget gas sensors, etc. You've got far better gas sensors hanging off the front of your face and far better audio sensors off the side of your head. So cells enter thermal runaway. You get gases and heat. Now, the first thing that can happen is the battery itself can explode. If not, those gases vent. And when they do so, because you produce a huge amount of gas, they are produced under high pressure. So you get this hissing and screaming after the popping of the blast caps or the bursting of the pouch cells. Now, usually what first happens is you see what looks like black smoke. It's not smoke. It's small particles of those toxic heavy metal nanoparticles from the cathode, nickel, manganese, cobalt. So you will smell a bit of a chemical smell and you will hear the hissing, screaming and popping, and you will see then a thick white vapor cloud. If that ignites immediately, then because it's at high pressure, you get these long rocket-like flames, 1,000, 1,200 degrees centigrade. Some commentators say 2,000 degrees centigrade. If it doesn't ignite immediately, you get the possibility of delayed ignition and a vapor cloud explosion. Then when it's all over, you've got stranded electrical energy, which means arc flash. We've had our first person killed by an arc flash from an electric vehicle in the States. Electrocution, and electric vehicles in particular have reignited hours, days, and even weeks after the initial incident. So some consequences. This is when the battery explodes. These Chinese firefighters know this vehicle is in thermal runaway. They're trying to cool it. Putting water onto an electric vehicle is like putting water onto the roof of your house when your kitchen's on fire, because the battery, the cells in the battery are so heavily protected. Just get rid of that, sorry. So this is when a battery explodes. And you see the shrapnel. Toxic fumes. This is an e-scooter that went into thermal runaway on the underground. The train pulled in to the Parsons Green tube station. They threw the e-scooter out, which was burning on the end of the platform. But you can see the amount of smoke. You produce huge volumes of vapor cloud and about half the volume of smoke, but that's still a lot. This is a single long compartment train. There's no compartments in it, right? Yet look at the amount of gas. And also listen to the owner.
Is there a fire extinguisher?
Fire extinguisher wouldn't work. We don't know the long-term effects of inhaling the vapor cloud or the fumes. Now this is if ignition occurs immediately. This is a single module. There's 24 of these in a Nissan Leaf, about 1.7 kilowatt hours. It's a nail abuse. Doesn't matter what form of abuse. You will see similar kind of responses from nail, from overcharge, etc. In this case, it's nail. That hammer weighs 23 kilograms. And these experiments were done at RAF Spadeadam over 3 weeks in the spring of 2021. And thanks to Envision, who supply the modules and actually have fully support my work with first responders. Now watch what happens to that hammer. So you saw the heavy metal nanoparticles first. People are buying second-hand electric vehicle batteries, including damaged ones. They're cannibalizing them and they're making domestic battery energy storage systems in their homes for solar arrays, etc. There are no rules and regulations governing where these are put. Imagine that in the attic, 55% are put into the attic, 5% under the main staircase. Imagine that in the airing cupboard on the 3rd floor of a terraced house in the bedroom cupboard. This is the rocket-like flames. Again, notice that's at shin height. Perfect to cut your leg off. This is what withdrew e-buses from the London streets. One e-bus amongst a bunch of diesel buses. Look how effective the water is.
Holy shit, man. It's scary.
There was also 2 e-bus fires in Paris, similar intensity, and that basically pulled the e-buses off the Parisian streets. Now, this is of concern. This is a domestic system that we mocked up. 8 modules, 8 cells in each, again Envision modules, about 13 kilowatt hours, a medium-sized one for the UK. What you can't see is the rocket-like flames impinging upon the concrete structure. But you can see the result there. Chunks of concrete being explosively propelled about 20 to 30 meters horizontally and 10 meters vertically, because water in the concrete is explosively vaporizing. And this is of concern because of the potential damage to car parks. 2 German cities have banned electric vehicles from their what's called parking houses, and the Brussels firefighters called for a ban following this. This was a car park that had actually been modified to allow for electric vehicles. Luckily, there was no other vehicles around, and they were able to deal with the fire, but you can see the damage. And essentially, electric vehicle fires cannot be put out. So let's move on to the vapor cloud. Again, this was work we did at RAF Spade Adam in spring 2021. It's again, abuse. It doesn't matter what form of abuse. What you will see first is the ejection of the nanoparticles and then the production of the vapor cloud. Following our work at the Fire Services College in 2020, we realized that if you only partially charge a lithium-ion battery, then ignition can be delayed or actually doesn't take place at all. So this module has been charged to 40%. We were trying to create a vapor cloud explosion, but as it turns out, we were below the LEL, so we didn't succeed. Now, I don't know about you, but I find this rather creepy. You always get 2 forms of vapor cloud, heavier than air and lighter than air. But only one dominates, and we cannot predict which one dominates. In this case, it's the buoyant form that dominates. You will see the heavier than air form produced. Now, the lower explosion limit is between 6 to 11%, and at this point we were below the LEL. But the immediate danger to life and health is well below the lower explosion limit. Now, the key point here is that you produce, from my research, both literature and applied, between 500 and 6,000 litres per kilowatt hour of the vapor cloud, and that does not include the droplets of organic solvent. There's a clear plastic blast wall behind us, which is why the light is dimming. Now you can start seeing the heavier than air vapor cloud. Again, imagine that in the bedroom cupboard. Imagine that under the stairs next to the fuse box, or up in the loft. Imagine that when people are sleeping. Remember, it's not just explosive, it's toxic. This is what happens if the vapor cloud actually deflagrates. This is a Tesla run over some debris, and the owner parked it in a garage in Shanghai. Took out 3 cars either side. From the first appearance of the vapor cloud to the explosion is 6 seconds. This is a new challenge. Every day I see new ones. Watch the car that comes across, collides, the electric vehicle spins, and there comes off the battery pack. The battery pack shoots off. Each day virtually I come across a new hazard. And of course it's not just big batteries that pose hazards either. This is a battery pack for charging this tablet. Notice how she tries to extinguish the flames with her bare feet. Not perhaps the best idea. Now, it's not electric vehicles that are killing people, actually. Yes, crashes are because they don't realize the acceleration. It's e-bikes and e-scooters. This is in Dublin. Delivery rider has just parked his bike outside a McDonald's to pick up a delivery. This couple go in and the bike starts to go into thermal runaway. There's the vapor cloud, which then ignites, and you start seeing debris being thrown everywhere, flaming debris, and also the toxic fumes. And notice how quickly it fills that section of the mall with toxic fumes. This is New York. If you listen to the commentary and look at the commentary.
Extraordinary amount of damage from this single bike that you can see here to my left. This call came in around 10:41 a.m. this morning. We are still here fighting this fire. We have over 50 units, fire and EMS on scene. We have over 200 members.
Our response time was less than 4 minutes. We quickly stretched a hose line into the building and started to extinguish the fire. The amount of fire that is produced by a single battery in just under 5 minutes we were unable to get ahead of it.
This is the smoke that's produced. This is in New South Wales. It's actual footage. 2 girls trapped in an upstairs bedroom. It's an e-bike that's burned, but look at the density of smoke and the visibility. The fire officer is unable to see anything, so he's having to shout to try and find the girls.
There's a door here. I'm gonna open it. What are you doing?
Happily, he was able to rescue them without any injuries. Again, every day something new. I'd never heard of a pressurized stairwell. E-bike burns. Occupant throws it outside of his flat, shuts the door. When the fire officers enter the stairwell at the bottom, it spreads the smoke throughout the stairwell. This is a growing and deadly problem. These e-bikes and e-scooters are killing people. They're injuring people. They're wrecking people's lives because they're destroying their homes. If an e-scooter or e-bike goes into thermal runaway in your home, you've got nearly an 8% chance of being killed, 64% chance of ending up in hospital. And this is entirely preventable by an education campaign. Do not charge these things indoors. If you have to, follow some simple advice. And because of that volume of vapor cloud that's produced, 500 to 6,000 litres per kilowatt hour, even e-bikes and e-scooters can cause vapor cloud explosions. This is in China. E-scooter goes into thermal runaway. You'll hear the popping of the blast caps on the cylindrical cells. The dog is the most sensible creature because unlike the human being who goes to try and turn the charger off, the dog decides that discretion's the better part of valor. Now, you get lithium battery energy storage systems in a whole range of places. You've got commercial domestic ones. You've got do-it-yourself domestic ones, which is my personal bugbear, and that's that one on the 3rd floor of a terraced house in the airing cupboard next to the hot water tank in the bedroom. Lithium-ion batteries start to go unstable at 60 to 70 degrees centigrade. You've also got them on hybrid and full battery ships and subs, and you've got grid-scale battery energy storage systems, and these will be in your area. They will be in South Wales, definitely. This is a do-it-yourself one in Poland with the vapor cloud coming off. We've had 5 commercial ones, residential ones in Germany explode. We've had 2 do-it-yourself ones in the UK. We've had 2 commercial ones in Australia, one of which the domestic system went into thermal runaway, but did not ignite and boiled off the vapor cloud. And the thermal imaging camera could not locate the heat source. And we've also had tens of thousands of these residential systems recalled in the United States, Australia, New Zealand, and the United Kingdom so far. Now, this is what changed the whole game. This was an explosion in Surprise in Arizona. The local fire service in Surprise did not know they had one of these battery energy storage systems on site. The smoke alarm triggered because, as per usual at that time, they were using a gaseous suppressant, which does not stop thermal propagation. It kills the fire, but the cells continued in thermal runaway. And in fact, there was no fire before or after the explosion. 1 hour after the smoke alarm triggered, in the remote monitoring station, the technician happened to glance at the monitor and realized that there was a problem, drove to the site and met the fire service who just turned up. So this is an hour after that smoke alarm triggered. They waited a further 2 hours with the firefighters going online to try and understand what a lithium-ion battery was, what the risks and hazards were, before they opened the door. 3 minutes later, there was a massive explosion. 4 firefighters were ballistically propelled in the jargon, 2 of them badly injured, 2 of them very severely injured. I talked to Fire Chief Tom Abbott about this, and he said they were lucky they didn't have 4 funerals. And this was the first time that we came across the fact that hydrogen cyanide was produced. The hazmat leader who'd been called in landed where that black spot is, 75 feet away. The safety masks of all 4 firefighters had just been disintegrated. Now, this is the eyewitness account of the hazmat chief. I make no excuse for this, and you'll see why in a couple of slides' time. He was the one that was ballistically propelled 75 feet. This is from the Underwriters Laboratories Fire Research Institute, UL, Underwriters Laboratories, FRI website. It's got brilliant material for firefighters, and it's free to use and join. So this is the eyewitness account of the hazmat leader.
Place. The door was opened, and Captain Clare used a thermal imaging camera to measure the temperature and determine if a fire was present in the structure.
We cracked the door. As we cracked the door, some of that white cloud started coming out from the top of the door. So it was expectant as what we were going to see. Hey, this cloud had been outside. It was still inside the building. It was going to come out. It was going to dissipate. Our readings started going the same way. We're getting the readings that we have. We're doing Draeger tubes. We're doing Draeger chips. We're looking at our readings on our things. Everything's hitting just like we thought. So I take the TIC camera and I take a step inside, as I told them we were making entry when we cracked the door. That was the time that I said we were making entry into the building. I did not enter the building like people are thinking. I stepped inside so I could tick down the road because I wanted to see what did we have going. I ticked the entire building. I came back, made a communication. I said 104 degrees, no active fire.
Captain Clare reported that the maximum temperature was 104 degrees Fahrenheit and that no active fire or visible arcing was present. A white gas vapor mixture can be seen pouring from the open door. The hazmat team monitored conditions from the doorway for approximately 3 minutes before the gas vapor mixture in the structure ignited and all 4 members lost consciousness.
At that point in time, we were backing back out so our crew could be safe. And I remember the last thing as we're turning around to go, I looked back at my TIC camera and there was something weird on it. To this day, I cannot tell you what I saw or what I looked, but I remember going, and I said, what is that? And boom, it blew up.
At the moment of the deflagration event, the firefighters outside the hot zone described hearing a loud noise and seeing a jet of flame that extended at least 75 feet outward and an estimated 20 feet vertically from the southeast facing door.
It was just a loud, sudden explosion, tremendous shock wave, and then a big fireball that went up the sky that I could see over the building.
Both doors blew off the structure, and Captain Clare and his crew were ballistically propelled against and under the chain link fence that surrounded the energy storage system.
I don't remember anything really for about the next month and a half. It's pretty foggy, but from all accounts, my 2 firefighters that were over here and back off the line got blown backwards. I think they went 10 to 12 feet, somewhere in there, maybe a little farther, 16, 20 feet. They got blown back that way. Justin got blown back this way, and I told you he was by the door. So the door got ripped off of his hinges, and unfortunately that hit his leg and did the damage to his leg and knocked him backwards. And I took the blunt of the explosion coming off that exhaust port through the door, and it knocked me back. I hit the post of the fence, went down, created a hole through the fence so some of my guys could follow me through it, right, as they got blown back, bounced across the desert a bunch of different ways and landed unconscious, unresponsive in a bush burning.
Please.
In a bush burning. At no time before or after was there fire. And it was only one rack out of 27 racks that boiled off the vapor cloud for that 3 hours. So much vapor cloud that it leaked out of the container. It rolled across the prairie, heavier than air vapor cloud, which is what the report came in. It was people passing on the highway saw what they thought was a prairie on fire, low-lying smoke. And only one rack, equivalent to a Tesla, 90 kilowatt hours, produced all of that vapor cloud. This is the number of incidents, excluding South Korea is the red line, including South Korea. Various reasons. The key point is there's been 56 grid-scale battery energy storage fires and explosions, the vast majority in the last few years. And they are coming to a place near you, I can promise you. Now, this is some brilliant work being done by Mr. Rob Crew, big friend of mine at the DNV site at RAF Speardatum. He's using a generic mixture, which is the same as lithium battery vent gas, the vapor cloud, without the droplets of solvent. So exactly the same, depending what range which end of the range you use, 500 to 6,000 litres per kilowatt hour. What you're going to see is equivalent to the vapor cloud from essentially a small e-bike battery or up to about a small domestic battery energy storage system battery. First of all, we look from the inside, and that's just amazing in itself, and then from the outside. That was we used a clear plastic blast wall, a thin, basically a fragile blast wall, but still the overpressure got to 0.3 atmospheres, which is more than enough to kill you, basically. Now, this is a near miss, and this is why I told you I've got no regrets about showing that full video from ULFRI. This is a near miss. This is a research facility. You've got a large space. In the top right, you've got a pod. In the pod, a electric vehicle battery pack has gone into thermal runaway without ignition. These firefighters don't realize, they've never been told about the vapor cloud hazard. They're completely unaware that this is anything other than smoke. So they are carrying out standard operating procedure perfectly correctly for smoke. They're going in and out of this facility, opening the door and letting oxygen in. Now, initially, what was produced was the heavier than air vapor cloud, but now it's producing the lighter than air, the buoyant one. And notice the visibility. Okay, so the fire officers are moving in and out, and on the fourth time of stepping out the door, this happens. Vapor cloud explosion. They were very, very lucky not to have lost their lives. Take note, guys and girls. The vapor cloud explosion is the understated hazard. And of course, you could easily find yourself, as they did, smoke diving in a highly toxic and explosive environment. And this is the same video I showed you at the very beginning. We had a thermal imaging camera trained on that module, and this is what it saw. It saw the temperature of the module never rising above 127 degrees centigrade, but the thermocouples told us it was actually at 600 degrees centigrade. So this is slightly different form factor. This is prismatic cells, that roughly the same energy as those modules I showed you. But now we're sending it into overcharge, and what you hear are all the prismatic cells bursting. This is a completely sealed metal box riveted together. There's the vapor cloud. 2 kilowatt hours. Now, pouch cells, if you overcharge, immediately ignite. Those prismatic cells did not immediately ignite. The blast caps vented, and what you got was a vapor cloud explosion. This is the same experiment from inside. Now, the point is, thermal runaway does not necessarily result in fire. You can boil off the vapor cloud and it may not ignite. The vapor cloud is produced by all lithium batteries. If it does ignite immediately, because there's huge volumes produced, you get rocket-like flames. If ignition is delayed, you can get a vapor cloud explosion. If you kill fire but do not stop thermal propagation by efficiently cooling the cells, the hazard switches again from fire to explosion. Now, we did a series of fire extinguisher tests. If you're interested, because I'm conscious of time, I'll tell you all about them. But the key point here was that Cold Cut Cobra prevented thermal propagation, but it took a fair amount of time, about a minute and a half, despite the fact that the operator, the fire officer, knew which module we were overcharging, the second bottom one. It did stop thermal propagation to the top 5 modules. Those 2 went, but he had to keep moving it around. So you've got to think about that on a car. If you've got a big battery and you don't know which cells are in thermal runaway, the undamaged cells will produce hydrogen and oxygen. Okay. But it did stop thermal propagation to the others. Liquid nitrogen was useless. F500 killed the fire within 7 seconds, and it stopped thermal propagation to the top 3 modules. But whether that's due to the surfactant plus water mist or just to the water mist, we're about to do new tests to try and investigate. AVD did not work. It did not stop thermal propagation, and we had to suspend the test because we were worried about vapor cloud explosion. And if you think about it, the way AVD works is it encapsulates the battery and cuts off oxygen. But AVD is like mud. It's a dispersion of vermiculite in water, and it keeps the heat in my view. So you cut the oxygen off and you keep the heat in. You know what's going to happen. So this is fire blankets. They do have a role, but you need to understand the hazards. These fire officers didn't. They think the smoke, well, they think the white stuff coming through the blanket is smoke. Therefore, it's not explosive. It isn't. They've thrown the blanket over an electric vehicle on fire. It's killed the flames, but the cells are still in thermal runaway because there's no cooling, and they're boiling off the vapor cloud. They then pull back the fire blanket. If there hadn't been a howling crosswind right to left, that fire officer could have been injured or killed. As it was, the only victim was his trousers. And I have to thank David Smith of fireblanket.com, very responsible, sent me this video to use with fire officers. They do have a role, but you must understand the limitations and the risks and hazards. And one of them is the flame shooting from underneath. This is tests done funded by the Austrian government. They had to abandon the test because of the flames shooting out. The Rosenbauer system punches a hole in the battery pack. Again, the test didn't work because the water just flowed back out of that hole. And they had to deflate the tires for the punch to reach the battery pack. Pouring water onto an electric vehicle in thermal runaway, which this one isn't in thermal runaway, is, as Matt Dedman says, like pouring water on the roof of your house when your kitchen's on fire. And if this is a BMW i3 dropped into a skip of water, the battery kept on igniting because the undamaged cells were producing hydrogen and oxygen, which can feed the flames or indeed assist in explosion. And this is why Tesla says, do not drop our electric vehicles into water. No extinguishers are actually recommended at the present time. This is in Humberside. Owner realized his car was apparently on fire, producing smoke. He backed it down the drive, jumped out, phoned the fire service. When they arrived, it was completely quiescent. This fire officer had no idea about electric vehicles. He's wearing a COVID mask instead of full BA, and he's using a foam fire extinguisher, handheld fire extinguisher. He's crouching just at the right height for those 1,000-degree flames to cut him in half. He also doesn't realize that the car has gone into thermal runaway again because the white vapor cloud is boiling out the back. Not his fault. Finally, a thought experiment. You come across a crashed electric vehicle, somebody's trapped. As you move towards it, you see or you hear a hissing and a popping, and then you see a white vapor cloud, a white cloud coming out. What do? I don't have the answers yet, but it's not a thought experiment. And notice the quote. This is from a fire chief in Australia. We only risk our lives for lives that can be saved. How long might you actually have? Six seconds. I hope you're not asleep. Thanks for your kind attention.
Thanks, Paul. That's been really informative and some really good thought-provoking information there, certainly for firefighters. In terms of questions, I didn't see many coming in. Gerard may jump in at this point if he's had any come in at his end. The only one I sort of pose to you, for Paul, is would conventional firefighting tactics be advised for vapor cloud? Obviously, when we talk about fighting fires within a compartment, we talk about gas dilution. Would you advise that for in and around vehicles firefighting?
I wouldn't advise you to be anywhere near a vapor cloud around a vehicle or anything else. From a safe distance, yes, diluted, lots of droplets of water into the atmosphere, diluted. The water will help prevent an explosion, and basically fogging out the gases. Yeah, but don't put yourselves at risk as those guys did, not for no fault of their own, you know. And of course, the nightmare scenario is somebody trapped. It goes into thermal runaway, as I've said. Then I think you're talking water curtain. You know, it's better that the person gets wet than there is an explosion that kills them or injures them.
No, that's fantastic. And obviously, you just mentioned there about vehicles that have been involved in the collision. Certainly within our fire and rescue service, we're obviously raising that awareness to our crews about that possibility. And what may be seemingly be a standard extrication of a patient from a vehicle with an electric vehicle, we may certainly be looking at a time critical extrication purely because of the thermal runaway.
Yes, you could. And also, of course, if you've got the dashboard crushed, then you can't use a ram to push it away because you might crack the battery case.
Yeah, that's great information. Thank very much, Paul. I'm having the time is up on this signal, so I'd like to thank you for your time and much appreciated, Paul. Hopefully we'll get to meet in person in the future, and I wish you all the luck in carrying on with your work and providing it to fire services. It's very much appreciated.
Thank you very much. My pleasure.
Okay. Cheers,
Buy
Paul.
me a
Thank
pint
you.
sometime. Cheers.
Cheers now.